Good afternoon. We're going to have a small talk about using TLS and SSL. I'm Thomas Herlea, and a few years ago I was a student in the course. Since then I followed along with the materials that were published. I probably listened to all the talks in the meantime, and I noticed that there seemed to be a slight gap in the range of materials presented. There were materials not on the math, well perhaps on the first day, but on the crypto. The crypto protocols that are involved in SSL and TLS were discussed, especially in a talk by Bart. Then just earlier today, I think you've seen the protocols, among the protocols presented, something about SSL and TLS. The libraries are mostly taken care of, stuff like OpenSSL and other libraries. But then there was one piece missing for developers, maybe an example on how to get it deployed, simple examples, but nevertheless quite securely. So that is why here, this is the level at which we're going to have the discussion at the end of this afternoon. I'm going to focus the lecture on security, not compatibility, not multilingual, and so on. But I don't think I will even be able to touch all the security aspects that I'd like to, in order to keep it simple. And who knows what security aspects we don't even know about, and we will discover this year, next year, and so on. So don't take this as this is how you have to do it. This is an example of something that works when you deploy it. Form your own experience and see what works and see what other constraints you have when you need to work with this. Mostly look at it as a journey in which we're not going to take the simplest way. We're not going to use tools that do a lot of hand-holding. And over the course of this journey, you will see possible mistakes that you can make, and you will see some things that can help you. And it's a story in 4 parts. The first one is probably when your organization wakes up, I think I'd like to have one of those padlocks on my website for, security. So that's how it starts. The playground I'm going to use, I've specified it here so you can install it the same way, and so you can work with versions where the code examples that I show work just by copying them in. So it's a Fedora 18, recently appeared. I prefer it because it has rather new versions of software. So you will see examples that are future compatible for a few years at least. And it comes with Apache 2.4.3, which is from the 2.4 branch. And that is useful because it comes with new TLS versions, new ciphers, and so on. In order to manage it, here you see the command, here you see the command for installing it and for launching it. Every distribution of Linux almost has its own way of launching these services. Some still use the init.d, System 5 style, others use upstart, others use system control. So I'm showing you the commands as they are in our playground. And also another useful thing to know is where this particular Linux distribution decides to put its document root, the web pages. That's this path, var www html. When you will want to try examples, that's where you will need to put your files. And with command line tools, I believe you're going to see more of what's going on under the hood than with graphical user interfaces. I know it's not particularly secure, but I will become root on the system now with this command, and this will save me a few characters on the slides later on. But you should probably just do a sudo every time I work from the root prompt. Okay, let's see. Once I've installed the web server and launched it with system control start, let's see if maybe SSL TLS just works out of the box. On the left side, you see the HTTP version works. You get to see the page that I created. On the right side, you will get an error message, unable to connect to the server. So there's nothing there talking TLS. Okay, let's see. We read the documentation, we figure out that we need to enable TLS SSL on the site. And that's done with quite a small number of commands. You install the OpenSSL package, you install mod SSL, and you restart the web server. The command is restart because you have added modules. So there it's not enough to just reload it, you have to restart. And we are going to refresh the browser, and it's going to turn from unable to connect into the connection is untrusted. So something has changed, but what exactly? What are we talking about here? If people who know Firefox know that if you scroll down, you will get the option to just go ahead even though the connection is untrusted. What that would get you is that between you and whoever you have this SSL session with, a third party, an eavesdropper, would not be able to eavesdrop and would not be able to change the communication undetected. But what it doesn't solve is who exactly the other party is. Now, if your packets really go to the network interface of your web server, then the other party would indeed be who's supposed to be, the web server. But if there's an attacker in the middle who's intercepting the packets and who's answering in the name of the web server, then the other endpoint of the SSL connection would be the attacker. And just forging through this warning screen does not get you any guarantee about who the other side is. So because of that, please, when you get into production with your systems, don't let it at this stage. We will see what the problem is, why we have this, but never subject your users to have to take the decision, am I going to go through with this connection or not? Because if you do, you train them to go through even when the attacker is at the other end of the SSL connection. So this is a screen which should never appear if you build your websites well. Let's see why it appeared in the first place. What's the problem with untrusted? If you dig in a little bit, Firefox will give you a reason, and it will say the certificate is not trusted because it is self-signed. That's a bit of a misnomer, because it's not the self-signedness that's the problem. After all, the browser comes packed with lots of certificates which are guaranteed to be correct by entities represented by other certificates, and it goes up and up and up until you get to a certain number of so-called root CA certificates. And those certificates are self-signed, and we trust them. So it's not exactly the self-signedness that's the problem here with the lack of trust. It should be that whoever signed this certificate is not trusted. I don't know them. Yes, it happens to be the same entity who signed as the entity who's represented in the certificate, but the important part is who signed it, not known. And when the browser asks about it, when they see that untrusted connection, what should I do? Go on. The browser, in fact, says, I don't know about this third party, but maybe you, the user, know. So if you're willing to vouch for the correctness of this other endpoint, that they're who they are, sure, press OK, press ignore warning, go ahead. And it even offers you Firefox in that screen where you add this certificate to the trusted one. There's a checkbox which is on by default, which says trust this permanently. So add this certificate permanently. So the idea is if you take responsibility and say, yes, I vouch for this certificate, Firefox is willing to forever trust it. Well, not exactly forever. You'll see until when, a bit later. However, I think the instinct of most users when they get such a screen and they have to click through to get what they came for, the most users will have the reaction, get out of my way. And they'll do whatever it takes to get to the dancing piggies or whatever they think there's on the website. So there's a bit of a miscommunication there. The user clicks go on thinking get out, and the browser understands I can trust this certificate forever now. You see that if it's the attacker's certificate, you're in for a problem for a long time. So another lesson to draw from here, which I also mentioned on the previous slide, avoid surprising the user with this kind of thing. Either you prepare such that you don't surprise the user, or if you choose the path with less preparation, then put it in the documentation for the user. It works perhaps when it's a new employee and they get the file with this is how you connect to the company systems, and there we have one of these self-signed certificates. And you explain to them you will get such and such error message, you have to click through. And even in the documentation you can provide some more assurance or teach the user how to ensure that it really is the correct website. Onwards, why are we talking about certificates? We didn't do anything about any certificate. We just installed it the way it was. In fact, we didn't do, but Fedora did. When we installed mod.ssl, the post-installation script for that package ran some scripts which generate a self-signed certificate, and then installed it where the web server looks for it, and the package also deployed configuration which points there. So when we restarted the web server, it took into account this newly born certificate that we had just installed. It's not secure, so why do distributions go about it this way? I think it's because they want to help users to get up and running fast. If you're a novice, if you're just doing experiments, it's okay to start having SSL with a self-signed certificate, and then as you learn, you'll figure out how to do it securely. And on the other hand, if you're deploying this in a professional environment, there probably is a script that does the installation whose next move after installing it will be to remove this self-signed certificate and create some kind of proper certificate for the site. So where's this certificate we're talking about? mod.ssl, with the installation, deployed this configuration file. And we're going to come back to this configuration file again and again whenever we need to configure or reconfigure SSL on the system. In this file, there are some interesting sections here. I've abridged it a lot. There's a listen directive. Don't be afraid of this. This just makes it so that port 443 has something answering it, and we don't get that unable to connect error anymore, the first one. And then there's a section on virtual hosts. All the IP addresses that the host has, if they get contacted on port 443, this configuration here in this virtual host section will govern how SSL works. And we turn the engine on, and we indicate two files here, a key file and a CRT file. The key file corresponds to the private key in this asymmetric cryptography setup, and the certificate contains the public key and the identity of the website. We will get into more detail with these. But this is what enabled TLS in Apache. When we restarted the server, this part of the configuration file is what made it listen on port 443. If we want to manipulate the certificates and create our own and sign them and so on, we need to learn a little bit how OpenSSL works, the command. It's, the command line of OpenSSL is a wrapper around the OpenSSL library. So the power is in the OpenSSL library, and the commands are just something like a shell around that to enable you to invoke those functions from the library from the command line. And some of the commands, the documentation, the man page of some of the OpenSSL subcommands even says this was never meant to be a CA, but people use it like that, so we continue supporting it. But there's much more power and flexibility in the library than at the command line. There's enough functionality for us to see interesting things. So OpenSSL does its work through subcommands. If you run man OpenSSL, there's a command summary section, and there you will see a whole bunch of commands that are available. And if you want to get into more detail about one of the subcommands, you type man subcommand. The options that the OpenSSL subcommands take are either in single dash format, so something like dash no out or minus no out. And this means when you output something that I've asked you to show me, then don't show me the input to. And other options can have parameters, such as this one. This one, dash in, indicates an input file. If the -in input file is not provided, usually OpenSSL takes input from its standard input. If the -out command is not provided, OpenSSL will display to standard output. Interesting thing is that you're then able to chain these commands with pipelines and so on. We will not use chaining, we will just use one command at a time. So let's inspect a little bit those certificates that were dropped there by modSSL with the OpenSSL command. We change directory to a place under which they are stored, and first we are going to run an OpenSSL command to see what website the certificate is for. So as you have probably guessed, the subcommand is 509, but as you have probably guessed, we indicate the certificate with the -in option. And what we want to see is the subject from that certificate, and we don't want to see the certificate itself on the output. And the output is going to look like this a little bit. Subject, then some information there, /cn equals localhost.localdomain, and / more information. I've omitted the parts that are not relevant to site certificates. In the distinguished name, which you've probably heard about if you've discussed a little bit about certificates, the distinguished name describes in a unique way who that certificate is for, who the identity is from that certificate. And the part used for websites is the common name part. So not country, not region, not organization, not the email address or anything like that. It's the CN, the common name, which indicates which host name this certificate is for. Okay, it's a dummy certificate. It's for localhost. This site will never be accessible as localhost.localdomain from outside. That's a conventional name given for the site for accessing from the same host. So it's clear, we can't use this to show the site to any other party from any other computer. It just works from the same site. Is it a self-signed certificate like Firefox changed? Let's train our OpenSSL muscles, see if it's the case. In this case, the command is, again, 509, same input certificate, and this time we're asking for the issuer, not the subject, and again, not to see the original certificate. And the output has something which seems to be the same. So there's a good chance, it looks like it's a self-signed certificate. In fact, to be sure that it's self-signed, we would have to look at keys and at signatures on hashes. It's not enough to just look at the common name. You can create two self-signed certificates for localhost.localdomain and use the key of one to sign the other. It doesn't make it a self-signed certificate. Am I going too much into detail? Is it clear that self-signed really means signed with the private key corresponding to the public key? All right, you're good. So let's look at keys then. With X509, I'm going to extract the public key, and this is going to be a block of text. I didn't have room to copy it in. And from the private key, I will extract the public key part. And when I here, the public key. When I compare those blocks of text, I will see that the hex values are the same, and that's when I know that it's indeed the key is the one that signed, the private key is the one that signed the certificate. Good. Now that you have seen a little bit how OpenSSL works, those commands earlier, those were not important to know. Those were more so you get a feel of how you work with the command OpenSSL. If you want to start generating certificates, there's a plethora of choices here. You can either install an extra package and use something like GenKey, or you have GUI commands that wrap around OpenSSL, which are available in Fedora, or you can install another set of packages which are probably more expressive, allow you to specify more things, and so on and so on. You even can do it with Java, and even OpenSSL comes with a few possibilities to do it. I'm taking the route to show commands that manually do each step of the way, and they're based on the make file that's quoted there. So generating another key pair than whatever the package generated when it was installed. this is the subcommand, genp key, and these are the parameters of it. We want to generate an RSA key pair, and we want to put the result in private/keys.key. If you remember from here, this is the directory to which all those subpaths refer. Okay, back here. So if we just run this command as it is, this one will not give any error, it will complete, but do we get a good key pair, a secure key pair? Let's see. The algorithm could have been a DSA key pair for the digital signing algorithm, but for that you have to do it in 2 steps. So for the demonstration I chose RSA, it's simpler. The key file format, which you can control, the output, is one which is accepted by Apache, so I'm happy with that. The key length, the default key length is 1024 bits, and I have a problem with that. According to the National Institute for Standards of Technology in America, who have a special publication which, amongst other things, recommends until when you can use, or until when you should use at the latest, certain key lengths. And according to the baseline requirements document of the certification authorities and browser manufacturers forum, and according to what Bart said earlier this week, we should give up 1024-bit RSA keys because the security margin is not good enough. Okay, so in that case, we decide that the length should be 2048 bits, and in a moment we will see how we get our wish. Also, the public exponent that is taken by default when you run the command like this, like above, without too many parameters, is 65,537. Now that's 17 bits, and in last year's secappdev, I remember Bart Planel saying that we should just choose longer public exponents. It's very often used 3. Sorry, 3 is a value that's often used, but in some circumstances it's possible to try to take the cubic root of something you see, and that means you have reversed something that was encrypted with a public key. It shouldn't happen. And since Bart recommends to use more than 32 bits, that's the kind of value I'm using in this command, which uses parameters that are recommended. So it's changed a little bit. I've added this, a private key option for the RSA algorithm to use 2048 bits in the generation of the key. And another parameter which instructs the RSA key generation algorithm to choose this one as a public exponent. So 65,537, the default value, that is much shorter than this. It has a 1 on this position and a 1 on that position. I've extended it so it's more than 32 bits. And now we have this hexadecimal, this hexadecimal representation of the key. It's a curiosity why we are choosing public exponents which have a lot of zeros in them. But does anybody remember from the course why that might be the case, or what the advantage is in that case? Okay. Many implementations use the Chinese remainder theorem and a square and multiply algorithm for exponentiation. So in the case of square and multiply, I'm taking the original value of the message, and I'm squaring it. If I had a 1 here in the public key, I would then multiply them. I square it again, I square it again, I square it again, I square it again, and I multiply amongst themselves all the squares of squares that correspond to 1s in the pattern of the key. And that means I get to exponentiate much quicker than multiplying with itself so many times. I rather square, and sometimes I multiply with an accumulator, square some more. And in fact, with this one, I will end up with lots of squarings, about 16 if I'm not mistaken, and 1 multiplication. Makes it easier on smartphones and phones and sensors in nature to not have to do too much work when they want to communicate over TLS. This makes it easy for the client side and a bit more work for the server side. what about protecting this private key? There are some options there that I have glossed over. If you run it like this, you will have to type in a password at the command line. And it makes sense, no? If a private key is generated, it should never be unprotected. Those of you who have been to the threat modeling talk earlier saw that John was lambasting people who put the protection key next to the private key, the passphrase next to the private key. So either we password protect the file, and we could even choose the cipher under which to protect it, for example, 128-bit AES in CBC mode. Or, but there's a disadvantage if you have a private key file protected like this. And the disadvantage is that whenever you start your Apache again and it needs to get to the private key so that it can start using it in TLS, somebody will need to be there to type in the password. Or, because OpenSSL and Apache are quite sophisticated, you can configure a program whose output will be used as the passphrase, or you can configure a program that will look on a smart card and get the result and put it in and use it as passphrase. Those are the options, and I think that's the more secure variant. Those are the options for protecting the private key with a passphrase. There's another option which is a little bit more quick and dirty, and that is you don't protect it, you don't protect the key, you just protect the file in which the key is and hope that your OS is hardened enough to prevent attackers from getting to it. And the second option is that before you do your generation of the key pair, you set the mask for Unix permissions for all the files you generate from there on. So they allow reading and writing by the owner of the file and no permissions by the other, by any other principal on the system. And you can even protect against the root user with SE Linux if the context, if the SE Linux context associated for that location here in private, if that one is defined such that Apache can read from there but other users can't, then creating a file in that directory, like we are doing it, will make it adopt that context. I had problems with this when I was testing the scripts for this course, because I had created the private key and the certificate in my home directory, and then I sudo copied them over there, and when I was trying to restart Apache, it wouldn't work, it would complain. And I had to dig to realize that the SE Linux policies were forbidding Apache from getting into users' home directories and getting to private content. And when I had copied my file from my home directory under Apache, in my eagerness, I had told the copy command to preserve all attributes. And that preserved the SE Linux context too. If you want to know more about that, that's a whole other chapter. It's another secappdev edition, I think. Once you have the key pair, you want to associate the public key of the key pair with the identity of the web server, of the website. And we're going to bind those two together, for now, with, again, a self-signed certificate. Why I'm going through this intermediate step is because that first error that you saw when we enabled TLS, that gave two reasons. One was that the certificate was untrusted because it was signed by an unknown entity. And the second one, if you're trying to use your nice domain name for the site, is that localhost.local domain didn't match with the host name. So you would get a second reason for complaint, namely that the certificate appears not to be for the website from which I got it. So we're first getting rid of the certificate for the wrong website problem, and then we're going to get rid of the unknown signer problem. Here we go. Let's say that the site, we want this to be the name of the site, Learn TLS Now. I've chosen a top-level domain that doesn't exist and that is short enough, so yeah, don't look this up on the web. You won't find it, I think. And this is the command, this is the simplest command for generating a self-signed certificate. It's going to put a lot of data in it that it takes from a default configuration file, and it's going to ask you for a lot of information. It will ask you for the distinguished name, so country, region, organization, organizational unit, your email, and among others also the common name. It will ask for the common name, and that's where you have to type in learn.tls.now. In fact, all the rest doesn't matter. You can leave it empty. If you get bored of typing in that all the time, you can use this option. The subject of the certificate, of the self-signed certificate, will be this one. And this is the syntax you have to use. It doesn't have to be double quotes, but it has to be /cn equals, and it ends with a slash. And the conventional file extension for certificates, at least the way I saw it on Apache and OpenSSL, seems to be CRT, certificate. Earlier, when we generated the key pair, the extension seems to be .key, but I've also sometimes seen .pem, which is an indication of the file format, of the encoding of the key. I think it's clearer if we use .key and just make sure that it is in the right format for Apache. And I didn't mention that even though I called it a private key file, there's enough information in it to derive the public key again. So if you happen to lose your certificate or delete it or something like that, don't worry, you can regenerate the public key, or you can regenerate the certificate and extract it from the private key file. Now, just as with the key pair generation, is this default command giving me a good certificate, or is it going to have problems? Because I aimed for shortness here, not for security. Let's see, default hash algorithm is SHA-1. I think that's only because I'm using a very new version of OpenSSL. I suspect that earlier or much earlier versions of OpenSSL may have used MD5, and that would be a problem. Don't use MD5 even though you can explicitly ask OpenSSL to create a certificate with MD5 for you. Don't use it because the attack in 2008 that whole team of people with PlayStation 3s used to get an official CA to sign them a site certificate for which they had generated the collision so that the signature was not only valid for their site certificate but also for their CA certificate, enabled them to sign valid certificates for google.com, for ebay.com, for any site on the internet. They were gentlemen and they put a very short validity period for that certificate, so nothing bad happened as far as I know, but because these CAs, of which they chose one, was still using MD5 to get the hash that they will sign, that CA was making it too easy for somebody with evil intentions to generate two certificates, one that seems harmless, that they send to the CA and have it signed, and another one that is malicious, for example, by being a CA certificate itself. Does it have other problems? Well, default certificate validity is... Okay. Here I'm just stating that the default choice that OpenSSL, the version I have, makes for certificate is SHA-1. You can use SHA-2 and SHA-256, SHA-384. You can use those, you can explicitly invoke them, but it suits me to use SHA-1. It's not broken enough for me to recommend not to use it, for cryptologists to recommend not to use it. So I'm going to stick with the default and keep my commands short, and they'll fit on my slides. The next point there is the certificate validity. 30 days sounds about good for a development certificate or a testing certificate or so, but if I'm going to use it for my site, am I going to want every 30 days to regenerate a certificate? No, not really. We want something longer. And something else that's interesting in that certificate, if we analyze it, is that there's a certificate extension there which says CA is true. So this certificate thinks it's a CA certificate. It's on a web server. It authenticates a site, a web server, but it's got enough information in it. It's made in such a way that it could sign other certificates too. I don't really want that on my website to be a CA. So the certificate produced with this quick and dirty solution is good enough for testing, good enough if you do it just you. You can add it in Firefox by getting that error message that I've shown earlier and adding it among the exceptions. But even though you're alone on your machine, it would be good to check that it's really the certificate you think it is. How do we do that? How we do that, I'm going to show you after we generate a better self-signed certificate. So I'm going to add the number of days for a year, most of the years. I'm going to change the configuration file here, this one. I'm going to change this file so that the certificate doesn't think it's a CA. I cannot do that on the command line. I'm going to have to change it in the config file. And this gives me the opportunity to start explaining to you a little bit about how the OpenSSL config file looks like inside. It's got basically assignments, sometimes grouped in sections. From the beginning of the file until the first section header, you've got some kind of global assignments. Then you start getting sections introduced by a line in which you get just a construction like this, square brackets and the section name. Both outside and inside the sections, you have assignments such as this. And this is one that we're interested in. Basic constraints equals CA : false. This is what I want to put in the file so that it stops creating me CA certificates when I just need site certificates. There's a section there predefined in Fedora 18, which is called v3rec, which already has this assignment, and it has another assignment which is used for limiting the uses that the certificate will be good for. So let's say I deploy a certificate on my site and I only ever want to use it on the site. That means that I would prefer having a way to turn off the possibility that somebody, anybody, me, my brother, my sysadmin, starts signing code with it or start signing emails. This is a certificate that I mean for the website, and so I'm not going to give it extra powers. So here we go. It can do non-repudiation, and it can do digital signature and key encipherment, but none of the other things that would mean code signing and email. And since this section already has some assignments that I like, I don't need to change the configuration file. I just need to tell OpenSSL when it creates the self-signed certificate to use this section. And I do that with this option, -extensions, and I give it the argument v3rec. If you feel like it, read the documentation, go into the file, define your own sections, put whatever you want there. A section, there's not much danger that the section will be used when you don't intend to use it. There are some pre-named sections which the subcommands of OpenSSL will look for, and in those sections you can say and go get some more assignments from another section. But if I just add a section there called Thomas, none of the commands will look at it by default. They will only look if I tell them -extensions Thomas. Then they'll go and look at my section in the configuration file. And here at the bottom, I've pulled together all these disparate options, and you can copy paste that option, that command onto your command line. You'll get a certificate just like we discussed it. In order to make it visible now, we need to move two files or copy two files. We need to put the key where the keys are. Actually, we have already created it there. And we need the certificate to also be in a directory where the convention on Fedora is to keep certificates. And sure enough, I made sure that the commands I gave you place the certificates there in the good point. Now, what remains to be done is to tell mod SSL not to look anymore at the localhost, local domain key and certificate, but to look at the new self-signed ones. And we accomplished that by going into this configuration file that I mentioned to you and replacing the values for these two directives with the paths to our new files. Before they were localhost.key and localhost.crt, now they are the new values. And in order to let Apache know about this configuration change, we issue, here's the command that you just need to copy paste on your command line. It's not restart this time, it's just reload. There we go. Now, we're still going to get the problem that Firefox doesn't know who signed the certificate, But at least now when we navigate to https learn tls.now, and I'm assuming the hostname resolution is done to our site, we will not get the complaint anymore that the certificate seems to be for a completely different site. It's just a signer problem. And that one we're going to solve by adding an exception in Firefox. But before we do it, let's make sure that we are really adding the proper certificate. First, we need to generate the fingerprint of the certificate as we have it on the file system. This is the command. x509 is the subcommand. It reads in the certificate that we have just generated. It outputs the fingerprint. And you should also use -no_out, but it didn't fit on my line. And your output is going to be a line that goes like this. It's much longer than that. In order to enable you or anybody else to manually express trust in this certificate, when they load it in Firefox, they need to reload it so they see the new certificate. They're going to get the warning. They're going to expand the I understand the risk section. They're going to click on add exception. They're going to click on view the certificate. And there in the window, I've cut it out here for you, is going to be a field like this. Fingerprints, SHA-1 fingerprints, bang, 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 it goes on. There's another one, MD5 fingerprint, but because we're trying to phase out MD5, I have not included it even in the screenshot. So if you compare what's here with what we had on the command line, they match. And so now I know that, yes, the certificate that I'm about to add to the trusted ones really is the one that I generated on the file system. If your friends are doing that, they have access to the Firefox dialog, but they don't have access to your command line. But they can call you, and you can have access to the command line, and you can compare these hexadecimal values over the phone with each other. The authentication is going to be done biometrically by each other's brain, by recognizing the voice. You have to be friends to be able to do this. And so now, in a delegated kind of way, your friend was also able to add this certificate to their browser. And for 365 days, Firefox will not bother them with things when they collaborate with you. It's a good enough solution if you have a small team of developers, maybe spread geographically, that need to access the same site and don't want to spend money on an even better certificate. So this one would be good for 365 days. And when you reload next time Firefox, this is what you had before, and this is what you get next. So HTTPS is there, and it works now both with HTTPS and with HTTP. Good. We can congratulate ourselves so far. Let's say we aim for a bigger circle of people than just friends. Maybe still not the whole world, but a controlled environment, an enterprise, a small company or a bigger company. You can't expect employees to call you every 365 days to ask you to go to the command line and read the fingerprint over the phone. So we need a better solution. Why I wouldn't use more than 365 days for a certificate is that 365 days is already a long time to protect that key. Why? Because the private key has to be present on the file system. Now, whether it's protected just at the file system level or with a password, a passphrase, as soon as Apache has read it in, it's kept somewhere live in memory. So in principle, attackers, if they breach your system, have time at their disposal to try to fish out the private key. And if they fish out the private key, they only need to go to your website and download the certificate, because the certificate is given to everybody who wants to talk to the website. And now the attacker has the private key and the certificate, and they put themselves in the middle and say, no, 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 I'm learn TLS now, talk to me. And a victim would talk without realizing it to the attacker in the middle instead of talking to the server. It's, like I said, it's there for 365 days on a server that's accessible either from the, well, at least from the intranet, and the intranet is full of script kiddies and worms and viruses, we should assume. And then eventually somebody else than you will have profit here. Okay, so we don't want to do this every 365 days, but we want to have the certificates valid for at most 365 days. maybe we should work with two levels. Maybe we should have a long-term company key pair that we defend heavily, that we only use for signing certificates, that we never keep on the web server or on any other server. Maybe we keep it on a USB stick, and we use it to sign yearly website key pairs. If there's a new website that springs up in the meantime, 6 months later, we can sign that for a year, starting from then, 6 months later. We can even use it to sign before it has expired, or before its certificate's lifetime has expired. We can use it to sign the next long-term key, so that whoever knows the public key of the long-term key pair from now will have a way to bootstrap trust into the next very long-term key pair. Okay, how do we protect it? We keep it on a USB stick in the safe in the CEO's office, and we only take it out under strictly controlled circumstances, only for signing certificates. We never put it on a computer which might be infected with viruses. So this could be a half-day ceremony. And in fact, they're called key signing ceremonies. Install a PC from scratch, never connect it to the internet in the meantime, bring the USB key from the safe, plug it in, run some commands that are documented ahead of time and that are understood and audited and so on. And even if the key pair is protected, no, if the private key is protected by a passphrase, you could split that passphrase between two people, two trustworthy people in the company who are not the CEO, but a second and a third trusted party. For example, Chief Technical Officer and Chief Information Officer. And each of them goes, types in half the passphrase, walks away. The other one goes, types discreetly in the other half of the passphrase, press enter, and now the key is unlocked. Neither of these individuals is able by themselves to start signing certificates. A new site certificate can only be signed if the CEO agrees and opens the safe, if the CTO agrees and puts the first half, if the CIO agrees and puts the second half. And with this kind of setup, maybe we can even afford to keep the keys for longer, like 5 years. How to achieve that trust that we did earlier with ringing and comparing the fingerprints? Well, since we are in a closed system in an enterprise, once we've done this certificate generation, we could take the certificate to IT, and then the private key goes onto the server, and the certificate goes on the server too, and the certificate also goes to IT. And from now on, whenever IT installs a fresh PC for one of the employees, they pop in the certificate, and this way the user can go to the site and never even see that first untrusted connection screen. Because the trust now has been put in there manually by their IT department. And you could do even more than that. If you have a bring your own device kind of situation, where IT doesn't get to put their own keys, but it's the users, you would want to have a way for the users to verify that fingerprint and accept it without having to call IT every time. And you could achieve that by putting the fingerprint onto business cards, or putting it into the company gazette, which is printed on paper, or having a receptionist having it available, and whoever needs to bootstrap trust and is at the customer site and needs to connect back to the mothership, I don't know if this is a fingerprint, but they can call reception, and they just need to check these letters and numbers with reception. So there are numerous ways to ensure that there's an authentic way to check that the fingerprint is correct. If that's done, then from then on you have 365 days, or however much is left of the certificate, trust in the website. By the way, again, with phoning the receptionist, voice-based biometric identification, authentication. All right, so how we're going to generate the keys, the key pairs, certificates, and so on slightly differently this time. We're not going into Apache's directory structure where it expects the certificates on Fedora. We're going to, this happens on the secure PC that's freshly installed, that has never been connected to the internet, in the CEO's office, with the CEO's safe ready to accept a USB stick. And we format the USB stick, mount it over there, and change directory to it so that I don't have long paths in all these subsequent commands. And we again generate a private key, algorithm RSA again. I'm going to call the file like this, company keys 2013.key. I'm going to passphrase protect it as opposed to last time. I'm going to tell it to use 2048 bits and to use this public exponent. The output is going to be some dots and pluses, output from OpenSSL, and then OpenSSL is going to ask us to enter on the standard input the passphrase. This is where the CTO goes, types in the first half, looks away. CIO comes, types in the second half, looks away. Admin or CEO presses enter. They do it again for verifying that it's been entered correctly. And once it's done, we have indeed a key pair file on the USB stick. It's never been on the computer. It's directly created on a USB stick, and it's protected with the passphrase. I called it 2013 because in 5 years' time, we're going to create a new key, and I don't even want the risk to have keys getting on top of each other and so on. Like this, we keep it neat and tidy. Now we need to use this key pair to create a self-signed certificate, and this time it's going to be a CA certificate. I'm going to use the days option with 5 times 365 days to have it for 5 years. I'm going to mention in the DN, in the distinguished named field, I don't have to put a website name in now. This is not a website certificate now, it's a CA certificate. So there I will put in Belgium, Leuven, Learn TLS Now company. This is the email address, info@tls.now, things like that. And I'm going to let it use that default section of the configuration file which bothered me last time, which made it be a CA. So the command will look like this. You can decrypt it on your own. You have enough information. Of course, this time it's going to ask me for a passphrase, because when it tries to sign the public key and the certificate with the private key needs first to be unlocked. CIO types in first half of the passphrase, then the CTO, then they press enter, and they generate a file like this, company cert 2013. Now, all good and well. This is a certificate that needs to get into users' browsers so they don't get surprised when, after a year, the site certificate changes. The site certificate can change as long as it's signed by the company CA, and the company CA doesn't change. And the company CA is already there among the trusted, so the site certificate change goes by transparently, unnoticed. How do we get it in? Well, here it's a mess. Many browsers do it in many ways. Perhaps the more elegant solution is the one on Windows after all, where you can install the certificate, the CA certificate, system-wide into a central repository where it's going to be used whatever users you create. On Linux with Firefox, unfortunately I didn't manage to do it. And I didn't manage to do it other than this. I need to use this command certutil, which comes in the NSS tools package. I install it on a system, and I'm going to scan all the user home directories. I hope that's where they are. In all the home directories, I'm going to look for .mozilla/Firefox, and then I'm going to look for a subdirectory whatever .default, because that's where Mozilla stores its profile. That's where where Firefox stores its user profiles, and it's in the user profile that I found out a way to add a certificate to the trusted ones. And this is the command: certutil add a certificate which is going to be labeled TLS now. Give it trust for websites, but not code signing and not email. That's what TCC means. take the certificate from a copy of the USB stick, its media, other USB, and put it in this directory, which is the set of Firefox profile directories. When I've run that command, the certificate has been added to all the users who had an account at that time. All the others have to go another way. I suspect that there's a slight mismatch in some versions among the tools that get deployed by default with Fedora. It's very possible that in the future there will be a much more elegant way where you can add a company certificate like this somewhere in /etc, where it's going to be taken into account globally, system-wide. Now that we have the workflow for generating, signing, and deploying the company, the CA certificate, let's see about the site certificates. I'm going to reuse the key pair that I generated earlier, and here's the command for generating a certificate signing request. Earlier, when I used OpenSSL REQ, I told it to generate a new self-signed certificate. Now I'm going to tell it to generate a certificate signing request. It is similar to a self-signed certificate, except it cannot be used directly on a website. Apache would complain if you try to use a certificate signing request, but it's understood by CAs. This is the format in which they expect certificate signing requests to come in. I've specified the subject again. It's the website this time, because this is a site certificate. And I'm choosing 1 year for duration, and I'm using the non-CA options section from the configuration file. And I'm outputting the certificate directly into... I'm outputting it not where the certificates are stored and not where the private keys are stored, but one level higher, so I don't mix up certificates with signing requests. Now, for signing it, this is a more complicated business, not enough room to illustrate all the details. You practically have to go in the configuration file this time, set values. More than that, you have to set up something called an index file and something called a serial number file. One is for keeping track of what certificates have been issued. The other one is to avoid repeating serial numbers. And these have to be files on the file system, or could be on that USB stick. And they have to be referenced from the configuration file. For this bottom part, by the way, we are again on the secure computer, because this is a signing ceremony. So this is what we do with the CIO, CEO, and CTO, with the safe, all that dance. A freshly installed computer every time. You have to be paranoid, otherwise it's enough for the computer on which you do the signing to have malware on it one time, and the game's lost. And here's the big hairy mess of options for turning that certificate signing request into a proper certificate, this time signed by the company CA. Last thing we need to do is to put the site certificate where Apache mod SSL is going to look for it, and to change again in SSL conf those files, SSL, here we go, the SSL certificate file and the certificate key file. When you change the name of those from, it's actually only this one that needs to change, from self-signed to corp-signed, I called it. Corp-signed, yes. So corporation signed. That's the only thing that needs to be changed, and Apache's configuration needs to be reloaded. And now everybody who has the company root CA among the trusted ones will seamlessly have a secure connection with our website. Now, sometimes it happens that on the same web server you have several websites, or you want to co-host them, or you are a company whose business it is to do co-hosting. Now, you need to be able to contact one IP address, talk to one web server, to one of several virtual host sections in the file, but you have the problem that the web server, with the slightly older versions and some extensions of TLS missing, will not know which site you're trying to access until it sets up the SSL connection so it can talk HTTP with you. But for setting up the SSL connection, it needs to know which certificate to dig up to present to you. So you could have 3 certificates for each of your 3 virtual sites, but when an SSL connection comes in, which one is Apache supposed to present for authentication? It's a bit of chicken and egg problem that has been solved with an extension to TLS, but that can also be solved if everything is under your control with aliases called alternate server names. So there's a mechanism, there's a convention which allows you to put into the certificate more than just a common name and more than just one host name. You would use, just as before, learn.tls now and put it into the common name with a -subj argument. And for these other 2, you would put them in the configuration file. So find the OpenSSL.conf file, find its v3req section, because that's the one we're already using, and add this. And now you've added these 2 extra host names. The directive is subject alt name, and the value will be DNS colon alternate hostname 1, comma DNS colon alternate hostname 2, and you can go on with more like that. And except for this change in the configuration file, the rest of the process is the same as before for generating the certificate signing request and then for having it signed by the company CA. You'd like to have a possibility, you've done your testing, you've done your intranet site, now you'd like to publish a site towards the outer world. How do you bootstrap trust with complete strangers? They're not going to call the reception, they're not going to call you to check fingerprints. Maybe they even live in other time zones and you don't want them to call them when it's day in their time zone and night in yours. But luckily, web servers solved this problem at the very beginning of when SSL was deployed. They'll preload, just as you learned in other talks during secappdev this year, they have some root CAs pre-deployed that they implicitly trust. And in fact, when you're installing Firefox or Chrome or Opera, you're not only installing software, but you're also installing trust, maybe even without realizing, in all kinds of CAs, which may be more or less diligent and which may be more or less corrupt or more or less hackable. But okay, that's not a discussion for this part of the talk. Right. In order to get your certificate signed by one of those CAs that the whole world knows about, you need to still do the certificate signing request, but change the step in which you used your company CA certificate to sign it with a process which depends on professional or commercial CAs like this. You might be asked to submit the CSR file through a web interface, or you might be asked to bring it yourself on a USB stick or carrier pigeon or whatever. It depends on the CA how they want to receive the CSR from you. They will also want to receive from you information about yourself, which we just put there in the distinguished name, but they might want to have, amongst other things, proof that it is indeed you who controls learn.tls.now. Because otherwise, it's your site, but I'm creating a certificate signing request with my private key pair, and I'm going to a CA, and I say, please sign me the certificate for learn.tls now. If they don't check that it's really me who owns learn.tls now, I now just have obtained a valid attacker in the middle certificate. I can now go between learn.tls now and any of you, intercept the communication, and use this certificate, which is valid and signed by a root CA, to pretend I'm the Learn TLS Now site. So the procedures for verifying that, yes, I am who I claim I am, and I am controlling the website. And an interesting attack is if if I'm not in possession of the private key, I can grab the certificate from your site and extract the public key and put it in a new certificate in my name and go to a different CA and say, this is my public key, please associate it with my identity, sign it. If they don't check that I have the private key that belongs to that public key, they will sign a certificate that, well, I would say it has some interesting applications. Learn TLS Now will suddenly realize that they are able to decrypt communications sent to my fake site. Or I might go and claim, hey, learntls.now has stolen my private key. They have it. It matches with my key. OK, so there might also be a payment involved for getting this done. Usually you pay more for a stricter verification. And then when you get it back, it's either a download or they send it to you by signed mail or by courier, or again, it depends on the method. And then you get that file, put it in this path like we were doing before. You change your SSL.conf to point now to your ca-signed.crt, and you're good to go. Now, I've started talking about how this verification, whether you deserve to have the certificate, has been done better or worse. And in fact, some would not ask for. It wasn't clear in the beginning years what exactly it meant to have a strong assurance that the right entity got a certificate. They would even have some kind of low price certificate with little guarantee, maybe as little as you control a certain email address that you have declared in the certificate. There would be no identity card check, there would be no company existence check, no ownership of the website check, and it would be signed with the public key or with the certificate of the CA, which is used for low security requirement applications. But did the browser know that? Not really. To the browser, it's just root CA is good. They have a sub CA that is certified by the main CA, and this sub CA has certified this site certificate, so I trust it. There was no information there, or not enough information there, to say this is a low trust certificate. This is not meant to be not meant to be used in high assurance situations.
There's no kind of information inside of the certificate. You're just saying that this certificate is only meant to be done to sign a kind of pages and not to sign another certificates?
Sure, but even among those things, there would be certificates signed for sites, not for signing code or mail. They would be certificates for which the CA has interrogated you and checked your mother and your father and done a background check that you really are you and you really own that website, whereas somebody else would have another certificate which was obtained by emailing it to a CA, to their low security signing procedure, who sent it back to the email address that was given in the certificate. Mm-hmm. And their idea is, if you receive it, it means you have control of that email address. So, okay, we know that there is somebody there. If we're going to have questions later, we're going to send complaint emails to that mail address, and we know you're going to receive them. And there's a big disparity between how much assurance you can derive from these two certificates. So people started realizing, wow, it's possible to get certificates with really low assurance, and this is a catastrophe, and how much trust can we still have in SSL and TLS? And there was a scramble. Okay, what do we do? Let's standardize to a minimum level of checking that is going to be done, and to make it so high that it's good for high assurance applications. And they called them extended validation certificates. what did they implement? Well, what in my opinion should have been implemented from the beginning, namely strong assurance that the identity and the public key belong together. And you can only get an extended validation certificate if you pass this validation procedure, and if the certificate is going to have an explicit link to what validation policy was used, and if there are certain extensions present there which are assigned to different CAs. So I think you have to be an extension validation CA to produce extension validation certificates. And it's up to the browsers which set of this elite CAs they recognize. It's a bit more complicated to get. You have to jump through more hoops, but also the assurance that you really are you is higher. So the GUIs, the graphical user interfaces of browsers, make the difference. In my screenshots, you just saw there a gray bar with a gray padlock. But if you get one of these EV certificates, in Firefox it's going to be a greenish button which mentions the company name. In Internet Explorer, it's going to be highlighted differently. Maybe the whole bar is green. There's a graphical distinction which shows that you can trust these even more. Okay, I already hinted to the fact that it's usually not the root CA which signs your site certificate. It's going to be a sub-CA. Why? One example that I gave before was they had different sub-CAs, one for high assurance, one for medium assurance, one for low assurance. Or it could be that they had one in Belgium, one in Germany, one in France, one in England, or for whatever other reason they want to delegate this certification process to a sub-entity, they can do it. This also means that when a browser will check that the public key of the website corresponds to the host name of the website, they will see there's a signature there, but it's made by the sub-CA's key. So they will verify that the leaf certificate is okay if the branch, if the twig above it is okay. That one they will verify with the branch above it, and that one they will verify with the trunk above it. And it has to keep going on like this until at the root of it, it's one of the trusted CAs that are already in the browser, preloaded. There was a vulnerability a few years ago, which I can't wrap my mind around it, how it could happen, where browsers were verifying only that the signature on the bottom certificate was okay. They were not checking the whole chain up. They would do one link. So, amazing. Do you remember, Ken? Can you confirm?
I don't. We've had various strange implementation bugs like that, but I don't remember that.
Yeah. It was quite trivial to fix, and of course the next patch to that software, the next update to that software fixed it. Instead of just making one verification, they had to do a loop to keep going to check it. Okay. Now, for space constraints, browsers are most often preloaded only with the root CAs. I'm not sure that in the era of cheap hard disks nowadays that's true, but you could implement it that way. That's the only thing that is required to be there. Anything more is an optimization. So the root CA is there, and the website has its own certificate and knows where it got it from, and checked that the signature is correct by getting the certificate of the sub-CA. Now the TLS protocol says provide the whole chain of certificates from your site certificate all the way up, except perhaps for the root CA, because that's already in the browser. And if that's not in the browser, you have other problems. So during the TLS protocol, you have to be able to provide the whole chain. In the case of Apache and mod-SSL, that means that you put the intermediate CAs, the sub-CAs, the sub-sub-CA certificate and the sub-CA certificate, you concatenate them in this format, and you put them in the file that is referenced by this directive, SSL certificate chain file in the SSL.conf configuration file. When you've done that, you are okay even for these multi-link chains of certificates. Now what happens after the 365 days. Why did we even look for 365 days? Okay, I told you, because the server might be hacked. But there's also another reason. Even if the server was impregnable, the first time you serve your certificate, there is theoretically enough information there to recover from the public key and the modulus your RSA private key. We hope that it's very hard. We hope that factorization of large numbers is a difficult problem. But an attacker could simply be lucky. They might go, I'm going to try to choose this one as a factor and be lucky. First try. It would require incredible luck, but it's not out of the question. If they're not so lucky, they have attacks available for searching for this. And these attacks get only better with the passage of time. So that's why we are putting a limit to the length of the key, to the length of the duration of the window in which the attacker might be able to recover the private key through cryptanalysis. So they might have gotten it by deriving it, or by breaking into the server, or by trying enough candidates, or by beating up the sysadmin, or bribing him, or something like that. They might have gotten it. After a year, we want nobody to trust the key. That's why we have expiration. But what if we get proof that one of these things has happened even earlier? We need a sort of emergency expiration. And that's called revocation. And I think you've heard about it in the PKI infrastructures of BART. All right. That is usually handled with the cooperation of the certification authority. Because in your certificate, there usually are links towards either a CRL server or an OCSP server, which the browser is in principle expected to consult when they're checking if to trust or not a website. And so from your point of view, you need to let your CA know that you want to revoke your key, and they have to do the rest. And browsers should ignore that. Browsers should not take the view that not being able to contact the OCSP server is a sign that they can go ahead after all. They should stop the session. Yes, you're right if you're thinking that now all an attacker needs to do for a denial of service is to block access to the OCSP server. Yeah, that's why Bart was saying that building PKIs is really difficult. My last slide from Act 1. I don't know how much time I have for the other acts. Half an hour, right? Okay.
10 minutes, 9 minutes.
10 minutes, okay. Even if you have a padlock on, what can the attacker still do? They can lure you to HTTPS learn.t1s.now. If you find this in an email, if the font is funny, maybe you don't realize it's not TLS. If you click on it, you're going to the attacker's website, and the attacker could have very well registered the learn.t1s.now site and have proven to a CA that they are really in control of it, and they have a valid certificate. You're not being warned. Another attack. What if the attack lures the victim to learn.tls.now at attacker.corp? It looks to the unprepared user like protocol followed by host name followed by gobbledygook. But in fact, what's happening here is that this is the username and this is the host name. If you think that seeing attacker.corp may scare off a user, rest assured that that could be an IP address. And if you think the users might find IP addresses funny in the middle of a URL, there's another way of expressing 4.3.2.1, that IP address, as one big integer, this one. So these two things are the same, with the IP address 4 octets and the one with the big number. The countermeasures that browsers have come up with against this is to highlight the URL parts differently. The protocol looks like this. The user is going to be bold. The host is going to be italic. The path is going to be normal. So now you have a chance as the user, when you're looking at the URL bar, to say, oh, my site name is funny. It's not italics now, it's bold. And then maybe you look a little bit more and you realize, oh, this is that attack. And then luckily you don't continue using that site. Another attack that I heard of from Moxie Marlin Spike's talk in, I think, 2009, is when he thought, well, users expect a padlock, and the browser doesn't put a padlock in the user interface when it's insecure, but it puts a fav icon. So if I draw my fav icon with a little lock, maybe I could fool somebody. Who knows? Statistically, a percentage of the population may fall for it. So what browsers do nowadays is that they don't put the favicon where the padlock would be if it was secure. Maybe they put them at opposite ends of the address bar. A common name attack, an attack on that common name part, was one that Bart Pernell showed you, I think, during the network protocols part. Okay. So I'm sure you understood why that worked and how it was remedied. How about this attack? It's another attack against the common name. An attacker is going to register a Unicode domain with characters that look like slash but are not slashes. Here, I dug up 4, and there are probably more, 4 Unicode points that look like a slash, more or less. So now I'm going to go to a registration authority, or I'm going to buy a domain with this name, learn.tls.now/ignore/attacker.com. And with this, I can then go to a CA and obtain a legitimate certificate. And then I can send an email or something with this URL to the user. And they might think they're going to learn.tls.com, their site, and they're browsing to the path ignore/attacker.com. But in fact, they would be coming to my site. A way that European browsers deal with this is to show an ASCII compliant encoding, and Punycode specified by RFC 3492 is one of them, which turns a URL with non-ASCII Unicode characters in another URL which doesn't contain slashes anymore, and so that mitigates this risk of falling for the fake slashes. Okay, much quicker then, and please do stop me when I've run out of time. Once you got the padlock on your site, you're still not done. You need to configure it to work well. Maybe you've seen this history of the protocol versions, SSL version 1 not even public, 2 broken, 3, then 3.1 basically became TLS 1.0, attacks were found, TLS 1.1 was drafted, but nobody felt a need to use it. Then TLS 1.2 was drafted too, even that is not adopted. We should refuse, or we should have our web server refuse to work with weak versions of the TLS or SSL protocol. And I'm giving you the example to use. This is how you specify which protocol to use. So if you put this in your virtual host section in the configuration file of mod.ssl, then your website will only accept TLS 1.2 connections. The option is called, or the directive is called SSL protocol. There's a list of identifiers that you can use after it. If there are some browsers that still don't support TLS 1.2, and there are many, you're forced to still work with weaker versions against which some attacks exist, namely SSL version 3 and TLS version 1. I recommend not to use the value all for SSL protocol because this is wishy-washy. It's better to be explicit about what you accept. Like that, your configuration is going to be safe even when you install a new version of Apache, a new version of mod.ssl, a new version of OpenSSL. Be explicit about what you will accept. Why I didn't put here in the recommended configuration TLS version 1 and 3 is because of the beast attack that I hope I'm going to have time to talk about. Within each protocol, you can choose which ciphers you're willing to let your web server use. There are a whole bunch of ciphers because OpenSSL, the library, is a more generic crypto library than just for SSL and TLS. So it supports legacy ciphers like DES and you don't want all of those. Okay, how do we define them? There's a directive SSL cipher suite, which takes a specification string like this. First specification, colon, second one, colon, third one, and so on. If you have different areas of your Apache configuration files and they define at several levels the SSL cipher suite, then there's a mechanism for combining these, going out from more general to more specific, so that for each page the web server knows what set of cipher suites to accept. This, a specification defines key exchange, authentication, encryption, the mode of encryption if it's a symmetric cipher, and hashing. And an example of identifier is this big long one. There are several defaults that can be omitted. For example, RSA can be omitted, and you can just declare AES128-SHA. And this means that a key exchange and authentication is going to be RSA, and the mode is going to be cipher block chaining. There are wildcards. If you just take if you just take AES, it's valid for AES 128 and 256. You can combine wildcards to obtain a sort of AND filters. Okay, it's a whole complex syntax. If you just specify spec, then whatever the context had provided so far, you add a cipher. If you specify dash in a cipher suite specification, you remove that cipher from the list of allowed ciphers, but you're still allowing it to be added later, maybe by a more specific context on the website. If you use exclamation mark, you remove it and you don't allow it to be added back. And if you do a plus spec, then you move that cipher specification from wherever it was to where you put this one. So in essence, it allows you to reorder the ciphers as you go deeper into more specific sections. There are wildcards, and if you want to get a list of all supported cipher suites, you execute OpenSSL with the ciphers subcommand and -v. By all means, make sure that ciphers like e-null, which means no encryption, ciphers from the exp alias, which is compatible with export control, meaning 40-bit keys, 56-bit keys, completely insufficient, and legacy ciphers such as RC2, DES, and IDEA, make sure those are not supported. An example of how you could express that is doing it like this. You declare an SSL cipher suite. You first take all ciphers out of the list that may have been defined by the context, and then you add your own high security ciphers, medium security ciphers, but still out of those, take out RC2 and IDEA, and don't let anybody later to add them to you. You might wonder what exactly this all means. You've used aliases, you've added, you've subtracted. Take one of these strings and provide it to OpenSSL ciphers -v as a parameter, and it will list all the ciphers that still match. And those are the ciphers which OpenSSL will provide mod SSL to use in TLS connections. Tinker with this until you're comfortable with the set of ciphers that you obtain. In TLS 1.0, there was a design flow which enabled attackers to fiddle with the ciphertext and abuse the CBC mode of operation to slowly get bits of information about information such as session cookies until they had enough to be able to copy and clone the cookie and impersonate the browser. So ideally, because the design flaw has been remediated in TLS 1.1, we should forget about SSL v3 and TLS v1 and just use TLS 1.2 or at least 1.1. But if you're forced to use the two SSL 3 and TLS 1, like I said, you can still avoid falling prey to the beast attack, or you can avoid your users falling prey to the beast attack by not using CBC mode ciphers. Put non-CBC mode ciphers first in the list of cipher specifications. Once your non-CBC mode ciphers, once you have your list of non-CBC mode ciphers, the next in the list should be non-symmetric ciphers. The only one that's available, at least in the OpenSSL version that I had on the playground, is RC4. We know from earlier this week that RC4 has its own problems. It leaks bits of information about the plain text. It's not so good. I asked Bart Preneel which was worse, to have CBC mode or RC4, and he said we should just get rid of all of them. If you can't get around it, do support it, and then if you do a risk analysis and you decide that you'd rather have your visitors every now and then be victims to a beast attack than to deny them access to the site, then take the decision to bite the bullet, accept the risk, and support CBC mode among your ciphers. But you can force the order of preference. So you can force, as you see here, you can force the most secure to be taken of all that the browser supports. Normally, it's the most secure that the browser wants among the ones that the server supports. But with this SSL on or cipher order on directive, you turn the tables and you force the browser to take the most secure one, in your opinion, from the ones they support. A non-CBC mode is AES GCM. This is a wildcard for a whole bunch of AES-based ciphers which are in used in Galois counter mode. Next RC4, then high, medium, but still don't forget to eliminate RC2 and IDEA. I'm soon going to be done with this Act 2. In cipher suites, you again don't want to use MD5, but why? In fact, the attacks against MD5 are not exposed, that vulnerability is not exposed in the way it's used in TLS. However, because of how badly it's been broken for collision, cryptologists don't trust it for second pre-image resistance either. So they just say, come on, we have better ciphers. SHA-1 is well supported. So if you eliminate MD5, you're not going to be incompatible with the whole world. You have SHA-2 members, like Nelly said. You have SHA-3, which is new and which could start to be implemented. It could happen that both a browser and a web server support it, and then they will happily use it. You can't rely on everybody having it because it's not mandatory. SHA-1 is mandatory in TLS 1.2. And so, do you want to wait until MD5 is as badly broken for pre-image resistance? Like the world waited with switching from TLS 1.0 to the later ones? No, let's kill this beast now. Let's say SSL cipher suite, append to the end, an exclamation mark MD5 to get rid of all the cipher suites that rely on MD5. One day, we will have to do this to SHA-1 too. You probably saw at the Bart Preneel's talk the curves of how many bits of entropy there were still, how many bits of security margin were still left. It's going down, and it's only going to keep going down for SHA-1 too. I think I'll stop here. And thank you for the attention, and welcome any questions you may have. The slides will be available on the website and the recording. And that's it then. Thank you.